Okay, today we are doing notes number 7. We're going to be looking at absolute value functions, and we're also going to be talking about function transformations. And hopefully in class for a few minutes we already talked a little bit about absolute value functions. And then function transformations is one of those topics that once you learn it, you're going to apply it to every kind of function you learn about in your entire mathematical life from this point on. So that's super important. So while we're applying transformations today to an absolute value function, the concepts apply to any kind of function. Okay, so let's go over the definition of y equals the absolute value of x. We know absolute value is distance from 0, and we know that it has to be 0 or positive, it can't be negative. And we saw, hopefully, when we were looking at this in class, we saw that the graph goes through 0, 0, 1, 1, 2, 2, 3, 3, etc. So the right side of it looks like part of the line y equals x, and then the left side of it would go through negative 1, 1, negative 2, 2, negative 3, 3, etc. The absolute value of negative 1 is 1, the absolute value of negative 2 is 2, and so on. So we have the other half of the graph. Sorry, that should look straight. Let me try that again. A little bit better. So altogether it makes a V shape. And basically what we're looking at is a piece of one line and a piece of another line. And since we can break it up into two pieces, we have what we call a piecewise definition. Now tomorrow we're going to be learning more about piecewise functions, so this is just a little bit of an introduction to it. So what we can do is we can take the absolute value of x and break it up into two pieces. And in fact, instead of writing absolute value of x right there, usually what we do is we just write y right there. So for the right side, we get the line y equals x. But it's only when x is greater than or equal to 0. And then for the left side, we get y equals the opposite of x. And that's only for when x is less than 0. So that altogether there is what a piecewise definition looks like. You have your y, or whatever the name of your function is, then you have an open brace. I don't know why, but we don't close the braces when we're writing piecewise functions. And then we have the right sides of both pieces, and then we have the domain for each piece. And if it's going to be a function, of course it has to pass the vertical line test, so you can't have any overlap in your domains, or you would have overlaps in your pieces. Okay, so moving on, what we're going to do next is talk about the transformations that hopefully we saw if we were able to do the Desmos activity together. And I'll just show you real quick here anyway. We're going to describe the transformation in words using the proper vocabulary, and then we'll give an example of the transformation using y equals the absolute value of x, and then we'll give some other kind of example, and then we'll just talk about it in general. So first let's recap what we saw with Desmos. Okay, here's Desmos, and I really haven't practiced with it very often, so I apologize if I'm a little clunky with it. What we're seeing right now is the graph of y equals the absolute value of x, and then I'm also going to turn on another graph. This one I have labeled as y equals some number a times the absolute value of x, where a can be a number between 1, which would mean it's no different from our original function, up to 10. Notice what's happening to the graph. We're multiplying outside the absolute value signs by a number that's greater than 1, like we're multiplying by 4 or 5 or 6 or 7. And as we do that, the graph gets steeper looking because we're stretching it vertically. The larger the number, the more the vertical stretch. We're multiplying the y values by some number, multiplying the y values by 3 or 4 or 5 or 6 or something like that. And those numbers don't have to be integers either. Okay, now we're going to take a look at y equals b times the absolute value of x, where b is a number that falls between 1/10 and 9/10. And I just picked these numbers because they were easy fractions to type in, but it doesn't have to be a tenth. It can be anything that falls between 0 and 1. Notice that each of these graphs are actually shorter than the original one because multiplying something by a number less than 1 is going to make it smaller. So you have a vertical shrink when you multiply by a number less than 1 but greater than 0. Now we're going to take a look at y equals c times x, and c can be any number between -3 and 3 is how I've set this up. So if c is a positive, but it's less than 1, then we have a graph that had a vertical shrink. If c is a positive, but it's a number greater than 1, we have a vertical stretch. The graph got taller. And if c is a negative, if it's a negative, then it flips the graph upside down, so we have a reflection across the x-axis. And then if the absolute value of that negative number is between 0 and 1, you have a vertical shrink. And if the absolute value of that negative number is greater than 1, you have a vertical stretch. The graph is taller than it typically would be. Okay, next we're going to look at y equals the absolute value of x plus d. And d can be any number between -10 and 10 is how I've set it. Of course, it could really be any number, but I've just set it up to go from -10 to 10. So look what happens. As d gets bigger, the entire graph is just raised up higher. So that changes the height of the graph. It shifts the whole graph up that many units. If d is 6, the graph is shifted up 6. Now some people say it shifted the y-intercept. Well, yes, it did, but it didn't just shift the y-intercept, it shifted the entire graph. And if d is negative, it shifted it down. So we often say if you add a number, it shifts up. If you add a positive number, it shifts up. If you add a negative number, or if you subtract a positive, it shifts down. Okay, now let's take a look at the absolute value of x minus f, and I have f set to go from -10 to 10. So let's look what happens if f is positive. So if we're doing x minus 1, x minus 2, x minus 3, x minus 4, this one does not do what you might expect. It actually goes to the right. If you're subtracting a positive, it goes to the right. If it's x minus a negative, x minus -2, x minus -4, x minus -6, it goes to the left. But what you're going to see in the equation is going to look like x plus 2 when it's x minus -2. It's going to look like x plus 6 when it's x minus -6, etc. So you just have to keep that straight in your mind. That might be the opposite of what you were expecting. And then finally, we have all the transformations put together, and I can change the value of the coefficient in front, and that makes it taller for a vertical stretch. It makes it wider, or I should say not as tall. I don't like to use wide, but not as tall for a vertical shrink. And if it's a negative, you also have a reflection. And then if you add or subtract inside the absolute values, you shift left or right. And then if you add or subtract outside the absolute values, you shift up or down. Okay. We can show a lot of these same things with a graphing calculator. So if you have your calculator, you can just go into the y equals menu, and then to type in absolute value of x, you can go to Math, over to Num, and absolute value is the first choice, and then you can put an x in there. There might be a shortcut, so if you press Alpha and then Window, it takes you to F2. And F2 is a nice shortcut menu for a lot of things that might be embedded more deeply into other menus. Notice that the first choice is absolute value. So if I was back here in y equals, and I hadn't typed anything yet, I could go with alpha, window, and then choose absolute value, and it's just a little bit quicker way to get there. So I'm going to go to zoom and choose zoom 6, which is my standard viewing window, -10 to 10 on both axes. And because my window is rectangular and not square, there's a bit of a skewed view here. It doesn't look like these lines are at 45-degree angles, but they really are. You just have to understand it's the window's fault. So we could go back to y equals, and we could type in y equals the absolute value of x minus 3, and what do you expect to happen to the graph? Think about it, and now let's look at it. It shifted the whole graph down 3. And if you have the color addition calculator, you can look at multiple graphs and tell what's what because you have them in different colors, and if you press trace and your up or down arrows, you can move the cursor from one to another and you'll see the equation of the one you're on at the top of the screen. So suppose I go back to y equals, and this time we're going to do the absolute value of x plus 4. What do you think the graph is going to look like? And now let's look. So that one is shifted up 4, a vertical shift of 4, up from the original. And again, I can press trace and go back and forth and see the equations at the top of the screen. Okay, and so on and so forth. So we could look at a vertical stretch. Y equals 2 times the absolute value of x, twice as tall. We could do a vertical shrink. Y equals 0.3 times the absolute value of x. Okay, not as tall, vertical shrink, and so on. We could use a negative to flip it upside down. We could shift it left or right. Absolute value of x minus 3. What are you expecting to see? Is it going to be left or right? This one is the one that is often counterintuitive. So this is the pink one. If it says x minus 3, it's actually right 3, not left 3. Okay, so back into our notes. In words, if we have a vertical stretch, an example of that would be y equals 3 times the absolute value of x, would be 3 times taller than the original. Another example, let's say that we're starting with y equals x squared. We could have y equals 2 times x squared, and that would be twice as tall. And in general, we say that if we start with y equals f of x, and we change it to y equals some number a times f of x, where a is greater than 1, it's a vertical stretch. Okay, let's do vertical shrink. So an example of a vertical shrink using the absolute value function would be y equals 1/4 times the absolute value of x. That would be 1/4 as tall because all of the y coordinates are being multiplied by 1/4. And another example, let's say we're still using y equals x squared. We could say y equals 3/4 x squared. That one would be 3/4 as tall. And in general, if we have y equals f of x and we change it to y equals a times f of x, where a is between 0 and 1, it's a vertical shrink. Okay, now let's do vertical shift. So for an example, if we have y equals absolute value of x and we change it to y equals absolute value of x plus 7, it's going to shift up 7. If we change it to y equals the absolute value of x minus 4, it's going to shift down 4. So you would say vertical shift up 7 or vertical shift down 4. Other examples, if we're using y equals x squared, you could have y equals x squared plus 1 and it shifts it up 1. You could have y equals x squared minus 99 and it shifts it down 99. So in general, we're going to say that if you start with y equals f of x, and you change it to y equals f of x plus k, it's going to be a shift up if k is greater than 0, and a shift down if k is less than 0. Okay, and then we have two more. We have a horizontal shift. So an example would be y equals the absolute value of x minus 3, and that would shift right 3. Or y equals the absolute value of x plus 1, and that would shift left 1. Okay, we could have y equals x minus 4 quantity squared. Notice that the number you're adding or subtracting is inside the function. So it's inside the absolute value signs, or it's inside the squaring. This would be right 4. Or you could have y equals the y equals the quantity x plus 9 quantity squared, and that would be left 9. So in general, we'll say that y equals f of x changes to y equals f of x minus k. Notice I put the k in the parentheses, so inside the function. It's going to be right if k is greater than 0, because I subtracted a positive, like x minus 3, x minus 4. And it's going to be left if k is less than 0. So we're subtracting a negative, like x minus negative 2. That would look like x plus 2. And then let's also throw in there the reflection across the x-axis. X-axis reflection. Okay, so an example would be y equals the opposite of the absolute value of x. And of course you could combine it with other changes, so you might have a negative 2 there, or a negative 9 there, or something like that. Or you could have y equals the opposite of x squared. And in general, y equals f of x is changing to y equals the opposite of f of x. And that's going to reflect it across the x-axis. All the positive y values become negative, and all the negative y values become positive. Okay, I still want to work out a few examples with you, but I'm going to end part 1 of the video right now, and we'll do the examples in part 2.